While the methods discussed in the tutorial are the best means we have today to estimate arc flash hazards, they do not address all of the variables or risks associated with arcing faults. Engineering judgment is required for arc flash calculations, and the information presented in this tutorial should not be interpreted as a recommendation to work on or near energized conductors. Working on or near energized electrical conductors is never recommended and should only be done when it is impossible to de-energize the circuit. In this video, we will discuss the following topics: purpose of conducting an arc flash risk assessment, cause and result, arc flash risk standards, arc flash risk assessment procedures and processes, arc flash risk assessment examples using power tools, labeling and work permits, issues to consider, best practices, final thoughts, and resources. Arc flash hazard is a dangerous condition associated with the possible release of energy caused by an electric arc. Arc flash hazards are extremely dangerous and cannot be taken lightly. Some of the reasons why an arc flash risk assessment is necessary is to prevent worker injury or loss of life, avoid medical expenses, minimize expensive equipment damage and system downtime, comply with codes and safety regulations, avoid litigation expense, and insurance requirements. It is estimated that it costs $1.3 million for each fatal electrical accident, up to $30 million in direct costs such as fines, medical costs, litigations, lost business, and equipment costs. About 2,000 plus workers will be sent to burn centers this year. What are some of the causes of arc flash? Spark discharge from accidental touching of dropped tools or loose parts, inadequate equipment short circuit ratings, installation failure, over voltages, corrosion, dust, condensation, or contamination, improper work procedures, and lack of maintenance. Two primary factors create hazards by arcing faults: workers' close proximity to the arcing fault and tremendous amounts of energy. It is also important to note that energy released is a function of system voltage, fault current magnitude, and fault duration. Arc flash risk assessment estimate incident energy exposure from potential arc sources. To understand the purpose of an arc flash study, it is important to understand the difference between a traditional fault and an arcing fault. A bolted three-phase, phase-to-phase, or phase-to-ground fault creates high current that flows through the network and the current is contained within the network. Traditional fault studies are used to select equipment that can withstand and interrupt these short-circuit currents. Arcing faults occur when the current passes through the vapor between two conducting materials. These high-temperature arcs can cause fatal burns even when standing several feet from the arc. The electrical arcs also shower droplets of molten material in the surrounding area, causing further hazard. The arcing fault current is smaller than a traditional bolted fault current because the vapor acts as an impedance between the conducting materials. Here's an arc flash accident to demonstrate the enormous strength and destruction of a blast. To dive deeper into arc flash, we must first understand some basic terminologies. The determination of the incident energy at each equipment will provide guidance on the selection of personal protection equipment, commonly referred to as PPE. Incident energy is the amount of thermal energy impressed on a surface, a certain distance from the source, generated during an electrical arc event. Incident energy is typically expressed in calories per centimeter squared. According to the NFPA 70E standard, for incident energy equal to or less than 1.2 calories per centimeter squared, PPE of a long sleeve shirt and long pants or coverall, face shield, safety glasses, hearing protection, and heavy-duty gloves are required. An incident energy of 1.2 calories per centimeter squared is enough to cause second-degree burns. The working distance is based on the voltage level and equipment type. It should be measured from the worker's face or chest, whichever is closer during the work task. The shock protection boundaries shall be applicable where approaching personnel are exposed to energized electrical conductors or circuit parts. There are two boundaries, the limited approach boundary and restricted approach boundary. Here are some standards that pertain to arc flash safety, operations, procedures, and calculations. We will focus on the NFPA 70E and IEEE 1584 standards in this video. In regards to arc flash, NFPA 70E states, appropriate safety-related work practices shall be determined before any person approaches exposed live parts within the limited approach boundary by using both shock risk assessment and flash risk assessment. A flash risk assessment shall be done in order to protect personnel from the possibility of being injured by an arc flash. The assessment shall determine the flash protection boundary and the personal protective equipment that people within the flash protection boundary shall use. If live parts are not placed in an electrically safe work condition, work to be performed shall be considered energized electrical work and shall be performed by written permit only. Empirical equations on calculating arcing fault current, flash protection boundaries, and incident energy are provided in the IEEE 1584 standard. The formulas are valid for systems ranging from 208 volts to 15 kilovolts, bolted fault current between 700 amps to 106 kiloamps, and bus bar gap between 13 to 153 millimeters. Here is the process that is outlined in IEEE 1584-2002. First, collect system field data and installation equipment data to perform an accurate short circuit and coordination study. Determine power systems modes of operation, including tiebreaker positions, parallel generation. Determine bolted fault currents at each fault location. Determine arc fault current flowing through each branch for each fault location. Determine arcing duration time to clear the arcing fault current from the protected device settings. Record system voltages and equipment classes. Determine working distances based on system voltage and equipment class. Determine incident energy at each fault location. Determine flash protection boundary for all equipment at each fault location. Also take into consideration the tolerances of arcing fault current leading to different trip times and incident energy. Let's take a look at a real-life power system model and how to conduct an arc flash risk assessment using the Power Tool software. We will be looking at different situations and how to approach and mitigate the hazards. Here is an electrical power system that contains switchgears and motor control centers. We will look for any equipment that may experience an arc flash incident energy greater than 8 calories per centimeter squared. Afterwards, we will also make necessary changes to the system to bring the arc flash incident energy to more acceptable levels. We will be taking advantage of some powerful features in the software. The Scenario Manager can be used to create scenarios that reflect planned expansion, propose changes to protected device settings, addition of power factor correction capacitors, proposed adjustments to transformer taps, alternative tiebreaker operating positions, and so on. The Data Visualizer is another time-saving feature. It is useful for comparing results between multiple scenarios. Any combination of scenarios, components, and data fields may be displayed. Here we have a power system model that we are going to run an arc flash study on. At the top, you'll notice the utility, which is connected to a utility transformer, and this transformer feeds the main switchboard, critical switchboard, and motor controller center. We are going to run an arc flash study on all buses in the system, and we are going to look for any bus that has an incident energy of 8 calories per centimeter squared or greater. To run an arc flash study, click on the Run menu at the top of the screen and select Arc Flash Evaluation. You will see 3 tabs at the top of the window. The Standard and Unit tab will show you the different standards available to run an arc flash study. Within the same tab, you can also choose between using English and metric units. The second tab, the Fault Current tab, will allow you to change the max arcing duration, arcing tolerances, generator and synchronous motor contributions, and other options. And the last tab, Report Options tab, will allow you to report arc flash results for buses, protected device load side, protected device line side, check upstream devices for miscoordination, and other reporting options. This is the arc flash results spreadsheet for all buses. You can see all the buses along with the bolted fault current, the protected device arcing fault current, trip delay time, working distance, and most importantly, the incident energy. The protected devices are listed in the order that they clear the fault for each bus. For a more concise report, you can use the summary view. Notice that there are 3 buses with an incident energy of over 8 calories per centimeter squared: E switchboard, LPA bus, and switchboard. We are going to go back to the one-line diagram to identify these buses. We are now going to run a query to easily find those buses. To run a query, click Run at the top of the screen and select the Query option. There are many different queries you can use within the software. For this example, we are going to use the Arc Flash Incident Energy query. When we run this query, we will enter a value of 8 to identify all buses with an incident energy of 8 calories per centimeter squared or greater. Now you can see that those 3 buses are highlighted on the one-line diagram. We are now ready to perform mitigation on those buses. We will start by creating a scenario to work with. To do that, you can click on the project menu at the top of the screen and select Scenario Manager. We are going to call this scenario Proposed PD Modifications. This is the scenario we created. Any changes made here will not affect the base scenario. We will run the query again to find the 3 buses for us to perform mitigation. Here we have another look at the Arc Flash options, and we will leave everything the way it is and run Arc Flash. Here are the 3 buses with incident energies of 11, 15, and 23 calories per centimeter squared. We are going to focus on the first bus, E switchboard. Notice that the trip delay time is at 0.215 seconds. Let's see if we can reduce the trip delay time by reviewing the coordination protecting this bus. Here you can see 3 breaker curves protecting this bus. Breaker C switchboard MCB is the device that clears a fault at this bus. The vertical line is the arcing current that this device sees. The intersection shows us that the trip delay time is at 0.215 seconds. We can now try to change the breaker settings so that the arcing current line intersects at a faster time. We can start by dragging the instantaneous segment to the left. Notice now that the intersection is at a much faster time. When we look at the Arc Flash results, we can see the exact time of 0.018 seconds, giving us a new incident energy of 1 calorie per centimeter squared. Now let's look at the second bus, LPA bus. This bus has reached the maximum arcing duration of 2 seconds. For this example, we will take a look at the 1 line. We can see breaker 250A TYP is protecting this bus. You will notice that there is an upstream breaker as well. We can take a look at the upstream breaker and see if it is miscoordinated and trips faster than the downstream breaker. To do that, we will plot both breakers on a TCC drawing and compare. Here are the two breaker curves. We will now plot the arcing current line and review the intersection on these two breakers. Notice that the upstream breaker intersects much faster than the downstream breaker. To take the upstream breaker into consideration, we can enable this feature within the Arc Flash options. Notice now that the protected device displayed is the upstream breaker S switchboard FCB-4 with a trip delay time of 0.15 seconds. Our new incident energy is 1.1 calories per centimeter squared. Now let's take a look at our last bus, switchboard. It has a trip delay time of 0.36 seconds, with an incident energy of 23 calories per centimeter squared. For this example, we will implement an optical relay. To do that, we will go to the component editor and enter optical in the protection category. Now when we take a look at the Arc Flash results, the protected device name changes to optical. Notice that the trip delay time column for this bus is modifiable. Let's assume that this special instantaneous device trips at 3 cycles after initiation of the arc. Therefore, type in 0.05 in this field. With this trip time, the software calculates an incident energy of 3.4 calories per centimeter squared. Now let's run Data Visualizer to compare the incident energy between the existing system against the proposed design changes in the system. We will now select the base project and propose PD modifications to compare. We can now see the base project and propose PD modifications side by side for easy comparison. We can see that the E switchboard incident energy in the base project is 11.3 calories per centimeter squared and 1.0 calories per centimeter squared in the proposed scenario. The data visualizer also allows us to easily show result differences and comments. One of the goals is to develop Arc Flash labels. Here are some that are automatically generated from the SKM software. All text and information is customizable based on your requirements. You can also create Arc Flash labels in different languages. The label on the top right is in Spanish. Here's a work permit that is automatically generated from the software. It can be used to approve energized electrical work. Management can easily review all the details and make an informed decision. Here are some Arc Flash issues to consider: working distance, open or closed door, arc duration, voltage levels, PPE determination. There are other options in the SKM Arc Flash Evaluation that can affect your results. Those will be covered in a separate video. Here are some best practices to safeguard against arc flashes. De-energize equipment, minimize risk with good safety practices, refer to the latest NFPA 70E and OSHA standards for best practices, move the person further away from the electric arc. This can be achieved with tools and techniques such as remote racking or remote switching. The use of remote racking devices will allow the operator to move outside the flash protection boundary. Using new methods to perform the same job, for installing appropriate viewing windows or viewing ports of infrared scanning. Use current limiting protective devices. The arcing time is an important factor in the calculation of incident energy. Incident energy is directly proportional to arcing time. If the clearing time can be reduced, the incident energy is reduced in direct proportion. To be called current limiting, an interrupting device must interrupt the fault before the first half-cycle peak occurs on the fault waveform. Current limiting fuses are effective only when the fault current is within the current limiting range. Change the overcurrent protection to a faster tripping time. This can be easily accomplished with a device such as a Cutler Hammer Arc Flash Reduction Maintenance Switch or ARMS retrofit, which provides a simple and reliable method to reduce fault clearing time. Use or install arc-resistant switchgear. Utilize protective relays equipped with an independent protection setting groups. This allows a user to configure each group of protection settings for a different application. For example, the Cutler Hammer FP5000 protective relay, which is equipped with 4 independent protection setting groups, can be used in a simple control system to change the active setting group from standard to arc fault when personnel are planning on working with energized switchboards, panel boards, or motor control centers. Utilize zone selective interlocking where available. Although somewhat of a new phenomenon, the entire Arc Flash risk assessment process is both extensive and complex. Arcing fault energy is a function of current and arc duration. Arc duration is a function of the arcing current and the protected device type and settings. NEC requires Arc Flash warning labels. OSHA, through NFPA 70E, requires Arc Flash calculations and energized work permits. Workers are required to wear the proper PPE when inspecting and servicing equipment. Use the Power Tool software for ease of documentation, storing of equipment details, facilitate power system analysis, identify Arc Flash incident energy for each location, perform protected device coordination, schedule and track maintenance history, and more. Use SKM to comply with the latest industry standards. Make use of scenarios and data visualizer to evaluate different situations for the worst and best cases. For additional resources on Arc Flash and other study software from SKM, visit our website at www.skm.com, where you can find application guides, a power systems study specification, frequently asked questions, and more. You can also refer to the reference manuals on the software CD and also attend one of our many training courses throughout the year. Special thanks to the National Fire Protection Association, the Institute of Electrical and Electronics Engineers, CSA International, DuPont, and the IEEE NFPA Arc Flash Hazard Work Group Ad Hoc Committee.